Hello calculus students. Today we're going to be looking at our first definite integrals. So I called this an introduction to definite integration, and I think it's kind of quick and dirty. There's all kinds of different ways, different orders to do this in to introduce what a definite integral is. Today's is going to be like really basic and kind of shortcut a lot of the stuff that we'll have to come back to in the development of the theory. Okay, so we'll get into this on a deeper level as we proceed. So today we're going to start by just being told something, and that is, well, for instance, what's different about these integrals from the ones that we've seen already? What makes them definite?
They have numbers.
They have a little number. They have a place that they're at, very good, and that's because the lower number is called the lower limit of integration. The top number is called the upper limit of integration. And one thing that integration, like the most common interpretation of what it means, there are of course multiple ones, but the most common one that every calculus student knows if they've taken any calculus really, is that integration is the area under the curve. Now next week I'll try to explain why integration turns out to be the area under a curve. That's of course really useful to be able to find the area under not just like a circle or a circular curve or a trapezoidal curve, but any possible functions curve you can find with the integral. So we're going to do all of these today, these definite integrals, not by really knowing how to do them algebraically or with calculus, but by just thinking about the curve's picture and applying geometry. Does that kind of make sense? So when I look at this, it's the integral from 2 to 5 of this function with respect to x. That's all we know so far. All right? So what function is 3? What's it look like as a curve? It's just y equals 3, so it's just a horizontal line. So this is going to be really simple to do graphically. So I'm going to say start at 2, go to 5 on the x. These, by the way, are of course x equals, if that wasn't clear to you. Sometimes in integration later on, they can be other things, like in Calc 3, they could be x, y, or z, or theta, or all kinds of weird things, okay? But right now, this year, we're always going to just have x. And so this is 2, this is 5. The curve is just 3. There's my curve, y equals 3. So the integral means go from there and find the area under the curve. So of course this time it's very easy to figure out with geometry. What's the answer?
3 times 9.
It's just a rectangle, so the length of it is 3, the height of it is 3. So length times width equals 9. This one can also be done with geometry. This time we're going to go from 0 to 2 under this curve, which is just what kind of curve? Don't try to take the antiderivative. What is this curve? That's a good idea though. It's just a line, mx plus b. So I'll start by graphing my curve and say, all right, that's a line with a slope of 2 and intercept of 0. So up 2 over 1, up 2 over 1. And I could keep going, but where did the integral on this one say I'm particularly interested in? From 0 to 2. So that's going to be this area right here. So we just need to know the area of a triangle to figure this out. You guys know the area of a triangle, right? 1/2 base times height. So the base looks like it's how long? 2, and the height looks like it's 4. If you had a more sophisticated line, this might be more interesting, but that integral's value is 4 because the area under the curve, 2x from 0 to 2 is 4. And again, we'll get more into the theory of why this is area under curve another time. We're just trying to figure out how to do some basic definite integrals today, okay, with geometry or with our calculator. Having it cheat and do it for us. That's why I'm saying it's quick and dirty. These are quick and dirty techniques. Anyway, so I'm going to move these out of the way so we have a little more space to work with. So I argue that this curve is also a simple figure from geometry that you should be able to draw and then integrate. You guys help me draw this curve. It's not a horizontal line, it's not a mx plus b line, it's not a parabola or anything like that. What kind of curve is this?
It's a launch pad.
Good idea. It's a good idea, Courtney, but no.
It's
You guys seen this before?
yeah, it's a ellipse.
What's that? That's a circle. I argue this is that. Why?
Because you have a set of squares.
Yeah.
You see it now?
Yeah.
If you don't, hopefully you see it now. It's not the entire circle, it's just the upper semicircle, because I only have the plus and not the minus. And the radius of this circle is what? 2. So we're going to go from the origin, right? It doesn't have any transformations. It's a nice simple circle with a radius of 2 centered at the origin. So we'll draw it. Since its radius is 2 in all directions, it's going to look like this. And so the integral said this time to go from -2 to 2. It could, of course, say from -1 to 2. It could say pretty much anything. But these problems I'm giving you to begin with have to be doable with geometry without using calculus, really. So we're just thinking about what the calculus symbolism really means here. All right. So that's going to be half of a circle. So this guy's going to be equal to pi r squared over 2, which is going to be pi 2 squared over 2, which is going to be 2 pi. Remember, on all of these, I really should have been putting it the whole time. What are my units of the answer?
Units squared.
Units squared, right? Because we're thinking about area. Okay? So there are 3 definite intervals. You could also, of course, have a problem like this. I know I gave you a couple like this that kind of have a function that's a little bit more interesting, but it's still like all made of geometry that you can do. All right? So before we get to that one, I want to talk about one other feature of integration that's definitely going to come up. Let's use our calculator to investigate this one. So this is the other quick and dirty method, using our calculator to kind of cheat and do things numerically for us. So I want to figure out the integral from 0 to pi on the sine of x. I don't think we could do that geometrically. We're going to have to learn the fundamental theorem of calculus before we can do it using our antiderivatives that we've been learning already. So we're just going to use our calculator to figure it out. And then I'm going to ask you to go from 0 to 2 pi on the same function. We're just going to investigate the sine function a bunch. And then I think we'll go from pi to 0 on the sine function, just to figure out a couple other properties of definite integration. So we're going to do this with our calculator. Guess I'm going to have to. Oh, I did not think this through carefully enough. So anyway, you can see it well enough, I think. So we're going to go to math, and we're going to scroll down that menu until we see some calculus-y looking stuff. I believe this is how you can do, I think we've used this before, Math 8 is how you numerically do a derivative, Math 9 is how you numerically do an integral. If you have an older operating system, it might not show you the actual integral, it depends.
Alexis Ramsey and Kalina Barnes to student services, please.
But hopefully it shows you this. If not, just see me after class and I'll show you how to do it with yours. Okay? So we're going to do these numerically. We'll go 0 to pi on the sine of x dx. Now I'm also going to think about the picture still. So even though the picture is not really going to help me, it is going to help me understand what's going on here. So sine of x, you guys know, looks like this, right? Between 0 and 2 pi. Correct? So we're finding the area between 0 and pi in this first one. So that's what we're finding, right? Calculator's going to do it for us, though. And it turns out that between 0 and pi, how much area is there? 2. It almost put it in the right spot. Crazy. So any guesses as to what the area will be when we integrate from, instead of 0 to pi, 0 to 2 pi? When we go from here to here, you're going to have this, and you're also going to have this, because it's always the area between the curve and the x-axis. That's what the integral means. So what's going to happen there? Any ideas? Double, cancel, all good ideas. Let's just have the calculator tell us. And cancel out was correct. if you take in physics, this is like the principle of superposition, and it's completely destructive interference. So, this tells you something about situations like this. When you integrate the area between, or I should say the area under the axis is what? Negative. That's something that we've discovered, right? Using our calculator to cheat would help us out a little bit. So then let's think about this one. What's different about this last problem that I've written down? I guess I could draw it again. Here's the sign. This time I said our limits of integration are still 0 and still pi, but what's different? They're flipped in order, right? So if I do that, oh, come on, there we go. Should come out as -2. What does that mean? I thought that this was positive area up here.
It means that since you're going backwards.
So if I integrate backwards, like I've done here, integrating backwards is also negative. So I want to ask you, we won't use our calculator to cheat this time, thinking about this picture, what's the integral from 0 to -pi of the sine of x dx? Going to be, let's try not to use our calculator. We basically figured out that the absolute value under the humps of the sine or cosine curve, how much is space, how much is in there? A 2, right? So that we know that we're working with 2's on this problem. So what's this going to be? 2? Not -2? We're going back here now, right?
Negative and another negative, so it's positive.
So it's underneath, so that's negative. So if we went from -pi to 0, that'd be -2, but it didn't say that, it said backwards. So it's going to be -2, and flip it back to positive. Okay? And if you put that in your calculator, it'll tell you the same thing. So that's how you work with your calculator's numerical integrator. I just showed you how to do that. You've got some problems in your assignment that'll say use the numerical integrator, Math 9 or FNint in other words. And so that I think also will help us do some problems with something that's slightly more complex, and then we'll be done for today. So, our last question is looking at this curve which combines some elementary lines. It looks like we have a semicircle again, right? What is the area under the curve from -3 to 6? So how are we going to do that? Well, it's like from here, all this, right? And then I think we're still going to keep going all the way to 6, all that, and then all of this too. So you could do a trapezoid in a circle, you could do a rectangle, a triangle in a circle. It's up to you. But I just recommend using the rectangle, the triangle, and the circle. But since you're with me today, I think maybe we're going to have to use trapezoids quite a bit coming soon. So maybe we should remember the area of a trapezoid. It would be good to review, all right? So this trapezoid is going to be negative or positive?
Negative.
Negative. So area of a trapezoid, do you guys remember? It's got a half in it. Half.
Base 1, base 2.
Yes. In fact, let's do it over. Can I just like write it equal this way since I'm out of space? So it's going to be -1/2 base 1 plus base 2 times the height. That's the area of a trapezoid. And then we're going to have a circle. Is that going to be positive or negative on this picture? Positive. So it's going to be pi r squared, but it's a semicircle. So that's the answer. We just have to plug in our numbers. So we've got -1/2. What's the first base of this trapezoid? So 3. Is that this? And then that's this, and that I'm going to think of as my height. Yeah, so I think 3 sounds good. plus base 2 looks like it runs a little farther, right? 5. And the height looks like 3. Plus pi times the radius of this circle looks like it's 2, just like that last one, right? So this guy is going to be 8 times a half is 4, which is negative, plus 2 pi. So I'm going to get 2 pi minus 4, whatever that is, for my overall integral on this one. Okay? So how about same function? What if we go from 2 to 0? Remove that. Kind of already spoiled. I guess I could use green for this guy. 2 to 0 would be here to there, right? This area. What's that going to be?
Mr. McGee, you forgot to multiply by 3.
Oh, did I forget my 3? I did. Thank you. So it's negative 12. That makes sense, because this is going to be like 6 minus 12. That's going to give me negative. It looks like I have more negative area than I do positive over there. And I think my circle's actually not to scale. It actually looks a little too big. So, thank you. How about this one, though? When I go from 2 to 0, is that the spot I'm looking at?
Negative 3.
So is it going to be negative or positive?
Positive.
It should be positive, right? Because it's underneath, that's negative. And if I go from here to there, that's backwards. So there's a double negative here, right? And I just need the area of a triangle. This time I could call that the base 2, that the height 3. So it looks like half of 6 is 3. Positive. Okay? How about this last one? What's weird about it?
Just 1.
It just says go from 3 to 3. But if you go from 3 to 3 on any function, whether it's this or anything else, are you going to accumulate any area? No. So that answer is 0. So that's another like property of integrals, but I think it's just like a duh property, so I don't really think of it as a property. You know what I mean? So I think that's all you need for this assignment for 4.3 in our textbook anyway. You might see some problems where you have something like this and it has like a transformation. So I'm not going to do a problem like that, but I'll talk about it real briefly. So for instance, if it said like on this curve go from like 2 to 7, on this curve shifted up by 7, there's different ways to deal with that, right? You could think about this curve moved up by 7 and like try to redraw it or think about what it is in your head. But remember, you can also like do things by distributing the integral. So you could go like distribute this to f of x and to 7 and figure this one out as just the area of it under the curve 7 from 2 to 7. That's going to be 5 times 7 is 35. That's 35, done. And then do this one with a picture. So remember, you have different options. I've taught you a couple different things. We're combining geometry with a little bit of algebraic distributing, and this new idea of the area under a curve is the definite integral. See you next time.